Hello everybody, I'm Gleb and right now we're going to talk about 5G power control. But before we're going to start talking about that, I would like to start with basic questions. Why we need power control in wireless networks? So there are multiple reasons. The first one is that network should manage intra-cell interference between users. The second reason is to support quality of service, quality of connection. And in addition to that, in real networks, we have user mobility. So what does it mean? It means that pass loss can vary from the distance, from the time, and there are maybe some obstacles between user equipment, between phone and base station. So all of this should be managed, and that's why in uplink we can use open loop and closed loop power control. Basically, open loop and closed loop pretty similar to 3G, to 4G, to 5G. It's basically the same. So that's why it's very important to understand what does it mean open loop and what does it mean closed loop. Let's start with closed loop, with open loop actually. Open loop happens in idle mode. This is very important. Idle mode, this is when user equipment wants to establish connection to network and send preamble. So open loop power control needs to calculate from reference signals from base station to calculate the pass loss and to read information that was sent from base station, read information about maximum allowed power in the cell from user equipment side. So after that calculation, user equipment can calculate power that can be enough to transmit random access channel with preamble to base station, that can be enough from base station side to read, to decode that message and understand it clearly. And at the same time, this power must not extend the maximum allowed power that was configured from base station, from network. And at this time, this power should be enough to not to interfere with other users, not to make intra-cell interference. This is open loop. Actually, can be quite confusing because there is no any loop, as you can see. There is no feedbacks, because loop is when we have feedbacks, but there is no feedbacks. There is indirectly commands, we can say, just indirectly. User equipment can only understand reference signals and information from base station. That's the only thing. When it comes to closed loop, there is a loop, there is feedbacks from base station. So closed loop happens in connected mode. This is very important. Closed loop is used for supporting quality of signal, and at the same time, again, about intra-cell interference managing, about minimizing such type of interference between users. So when user equipment has already established connection with base station, user equipment may send data and control information via channels. So base station can measure that channels from UE, from particular user equipment, and give special TPC commands. So this is transmission power commands to user equipment. if power is enough for base station to understand, this will be keep the same power command to user equipment. If base station cannot fully understand the message, it will send the message to increase the power to user equipment. If it is more than enough power for base station, yes, base station can give the command to decrease the power for user equipment transmission, for uplink transmission, because too much power will definitely lead to interference between users, and this will drastically impact on uplink throughput, impact on uplink services. So again, closed loop about connected mode, open loop it is about idle mode. Okay, and right now let's move to 5G downlink aspects. And right now let's talk about power control in downlink in 5G system. Actually, there is no power control with feedbacks in downlink direction, because base station, it is just a single node that broadcasts signals to multiple users in different locations. So it is possible to manage with feedbacks power from user equipments, yes, but user equipment cannot manage the power from base station, and at least I'm not aware about such technologies. I'm not sure that it is possible. Let's look at this diagram. This is relevant for 5G downlink signals. Basically, as a kind of a reference, let's say, we can take secondary synchronization signal with the range from minus 60 to plus 50 dBm energy per resource element. With the same power transmits physical broadcast channel and DMRS of physical broadcast channel. Plus 3 dB, we can boost physical, primary synchronization signal. With some adjustments from plus 8 to minus 8 dB, we can transmit physical downlink control channel. Actually, for that channel, I know that can be applied some kind of a dynamic control, dynamic adjustments based on block error rate. It is possible. Then we can transmit CSI-RS signals. For different cases can be different numbers. PDCCH channel is a little bit lower than SSS signals and PDCCH channel. PDCCH DMRS transmits with can be transmitted with some lower or the same power. Phase tracking reference signals again can be boosted from 0 to 7.78 dBm. The main thing that we should know and understand that if we want to boost some reference signals, yes, in order to increase the downlink coverage, in order to solve some problems in downlink direction, we basically take the energy for boosting from other signals. So there is a kind of a law of nature, yes, that the total power remains the same. And if we take some power from some signals, only in that condition we can boost our reference signals in downlink direction. This is very important to know and understand. Actually, in 3GPP, you can find some special tables, kind of a lookup tables for different configurations, for example, for DMRS, PDCCH, or for RS signals. So for some specific configurations, you can set specific powers for transmitting such signals. And now let's move to aspects in uplink for 5G system. It is more complicated to optimize the power from user equipments, the power in uplink direction, because uplink powers affects not only in power throughput, but also it affects to channel quality estimation, and this is very important. So, as I said before, 5G power controls is pretty similar to 3G to 4G networks. Random access channel use open loop power control techniques. PUSCH, uplink shared channel, and a sounding reference channel used closed loop techniques, and transmitted power control can be based on uplink signal to noise ratio, or it can be based on power headroom reports. Actually, there can be difference. For some cases, we can configure DCI commands via PDCCH. So I mean TPC commands, and these power commands can be the same for PUSCH and sounding reference signals. They can be, the DCI commands can be absolutely the same in order to achieve coherence between that signals. So, but in other cases, if we need, we can configure sounding reference signals with another DCI commands in order to make it kind of a separate estimation and transmission. So physical uplink control channel, it is also used closed loop TPC commands based on signal to noise ratio. And as I said before, TPC commands sent via DCI, PDCCH channel. So it is commands from base station. Adjustments. This is very interesting, I think, because adjustments can be from -1 to +3 dB. I mean, at one step. That's very interesting because for increasing, we can increase faster, we can increase more power for one step, for one interaction. That's very interesting because in real networks we should mitigate some impacts from user equipment mobility, from shadowing, fast shadowing. So increasing power is more important, we can say, because we can send commands for decreased power only in case of there is too many interference from other users. So supporting connection and increasing the power of user equipment is, we can say it is more important than decreasing the power of user equipment. So that's why different numbers you can see here. That's pretty interesting. And I would like to say that there are two types of supporting user equipment power in uplink: conventional and fractional. Conventional can be supported by physical uplink control channel. Conventional, it is when UE can fully compensate path loss, at least to try to fully compensate the path loss. And it doesn't matter how far the user equipment, what the calculated path loss. So the main aim in such scenario, in such configuration, is to maintain the required signal plus interference plus noise ratio. So such scenario can be supported by PUSCH and PUCCH fractional power control for uplink channels. User equipment in this scenario can decrease power for cell edge cases, for cell edge scenarios, in order to minimize the overall interference, the average interference for the cell. And by this decision can be achieved more uplink throughput at the cell level, but user's throughput can be a little bit lower. So as you can see, fractional and conventional power control can be used for uplink shared channels and sounding reference signal because it's pretty important to maintain the throughput for cell level. And control channel in uplink supports only conventional power control, because it doesn't matter, we don't talk about PUCCH throughput. We should be confident that in any cases UE try to fully compensate path loss for PUCCH, yes, for control information, and try to maintain the maximum available SNR. So that's why this is a difference. And right now let's talk about other aspects in 5G networks. As I mentioned before, in 5G it's possible to have beam-specific power settings. It is basically P0 parameter. It is UE nominal power. It refers to power for a subcarrier spacing 15 kHz. And alpha parameter. When 0, it means conventional power techniques, and 1, it means fractional power. So in 3GPP you can find special formulas for each channel that can contains P0 and alpha, and these parameters can be beam specific. So for each beam can be set differently. At least it's supposed to be so. Let's talk about some aspects for dual connectivity in uplink and uplink carrier aggregation, which is basically the same. So there are two cases for transmitting uplink power. UE is allowed to transmit maximum power for each carrier, and the second case is when user equipment must share power between carriers. So the first case, when UE is allowed to use maximum power for each carrier, it refers to the case when we can use, for example, ENDC, dual connectivity. Yes, is when user equipment transmit information for different bands, for different FR1 and FR2. ENDC FR1 plus FR2, yes, is when, for example, LTE band plus 5G millimeter waves. So in this case, user equipment will transmit maximum power for each carrier, for each channel. This is not so good in terms of power consumption, of course, but this is good in terms of uplink coverage. And the second case is when UE must share power between carriers. This is the case when we're talking about transmitting different carriers within one frequency range, just FR1, either FR2. So this is the case when we, for example, use uplink carrier aggregation only for FR2 or carrier aggregation only for FR1, yes? Or this may be the case E and C, where LTE plus, LTE plus 5G FR1. Why? Because LTE always refers to FR1, and 5G use FR1, for example, in our case, let's say C-band, yes? In this case, user must share power in uplink between carriers. So it was my basic overview of 5G power control techniques. If you like this video, you can like and subscribe to my channel. If you have any questions, you can ask me in a comments section below, or send me your question via email. So stand by with IoT Understanding channel. Goodbye.